I was reading about forensic data recovery, how they can pull a file off a totally fried hard drive just from these tiny magnetic traces.
Yeah, it's amazing stuff.
And it just struck me that what planetary scientists do is it's basically the same thing, but the hard drive is a planet, and it's been sitting in a radiation storm for 80 million years.
That is the perfect analogy for what we're looking at today. It's this paper from Pavlov and his team about the Curiosity rover. They're trying to recover the deleted files from a slab of Martian mudstone.
And what they found, or rather what they reconstructed, suggests Mars could have been much, much livelier than we thought.
Exactly.
But before we dive into the chemistry of it all, let's just take a quick moment to talk about our sponsor, Embersilk.
Oh, yeah. If you're looking to optimize your own data or automate parts of your business or even your life, you really should check them out.
They are experts in AI training, automation, and really just helping you figure out where these new AI agents can make the biggest impact.
Seriously, find them at embersilk.com for any of your AI needs.
All right, so they're building the future while we're here trying to decode the deep past. Let's go to Gale Crater, specifically to a rock sample they call Cumberland.
Right, so back in March of 2025, the team flagged 3 specific molecules they found in there: decane, undecane, and dodecane.
And these are long-chain alkanes, what does that actually mean for someone who isn't a chemist?
Think of them as fragments of fatty acids, the stuff that makes up cell membranes. On Earth, if you find these in ancient sediment, you're usually looking at the leftovers of life.
The leftovers of life, I like that. And this is but you can get these from just plain geology too, right?
Absolutely. Non-living processes can make similar molecules. So finding them isn't the smoking gun. You have to look at the context, at the whole picture.
And the context here is brutal.
Brutal is a good word for it.
Yeah.
This rock has been on the surface, totally exposed, for about 80 million years. Mars doesn't have a strong magnetic field, so it's just been blasted by cosmic radiation.
A process that just shreds organic molecules.
Right. It just tears them apart. So what Curiosity measured, something like 30 to 50 parts per billion, that's just the tiny fraction that survived.
Okay, so this is where the clever part comes in. The Pavlov team didn't just take that number. They built a model to, rewind the damage?
That's exactly what they did. They calculated the decay rate from the radiation and asked, okay, to have this little left now, how much did you need to start with 80 million years ago?
And the answer they got is the reason we're doing this deep dive.
It changes everything. The model suggests the original amount wasn't 50 parts per billion. It was likely between 120 and 7,700 parts per million.
Whoa! That's a completely different story. We're going from trace amounts to a rock that was originally loaded with organic material.
And that sheer volume is what makes the non-biological explanations start to fall apart.
Okay, so let's run through them. What about just dust from space? Interplanetary dust brings organics.
It does, but way too little.
Oh,
delivers
wow.
about 0.1 parts per billion. The math just doesn't work to get you up to thousands of parts per million. Not even close.
So space dust is out. What about geological processes on Mars itself, like serpentinization?
That's usually a good candidate. It's basically hot water reacting with certain rocks. But the analysis of the Cumberland sample showed it doesn't have the right minerals, like chlorite or serpentine, and it never got hot enough.
So the delivery from space is too low, and the local factory wasn't open for business?
That's the bottom line. Neither of those standard explanations can account for that much organic material.
Which leaves us with the one hypothesis that does fit the numbers.
Biology. I mean, if you look at ancient ocean sediments from Earth's Archean era, when the seas were just teeming with microbes.
Let me guess, the organic abundance matches.
It's a near-perfect match for what the model predicts was in that Martian mudstone.
That's incredible. So, to be clear, they're not saying they've found Martians.
No, it's not definitive proof.
Yeah.
But it's the first study to really show that a biological origin is, for now, the most reasonable hypothesis. It fits the data better than anything else.
It kind of flips the script. Instead of looking for a needle in a haystack, we found a haystack that looks like it was made of needles.
A great way to put it. And it gives us such a clear target for future missions. We need to drill. We need to find samples that have been shielded from all that radiation.
Because if we find these same alkanes intact, deep underground, that probability gets a whole lot stronger. What an optimistic thought. Our neighbor might have been teeming with life.
It really suggests that when the conditions are right, maybe the universe just defaults to life. It makes everything feel a little less empty, you know?
I love that perspective. If Mars could do it, just imagine what else is out there.
Exactly.
If you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.